All right, here comes the second part of lecture 4. Let me share screen. So, yes, so the first half, or the first less than half, I talked about estimating things from having observed the final outbreak. So assuming that the epidemic was over, we saw how many got infected, for instance, and then we estimated things. In many situations, that is not possible. For instance, in emerging diseases, which means new diseases that are currently going on, or for that matter, also very dangerous diseases, even if they have been going on earlier, it's not possible to wait until the end of the outbreak. We have to estimate the parameters and R0 earlier than that. For instance, as with the current ongoing COVID-19. So we now describe how to do this. And we focus on the situation not where the epidemic has gone half the way, but during the initial phase of the outbreak. So you should think of this, that we estimate maybe R0 from COVID-19, let's say after 1 month of the epidemic. Not by now, because now a fair fraction have become immune, but after 1 month, a negligible fraction have been immune. So consider the situation where we're in the initial phase and there is very little immunity in the community. So let's assume that we have a large community and that it is homogeneous and that we are in the beginning of an outbreak. Large is fine, beginning is fine, homogeneous is of course not true, but let's start with the simplest case. Perhaps I or Mikkel will say things about the situation when we don't have a homogeneous community. That we are in the beginning means that few people have been infected, or at least perhaps not few people, but the fraction infected should be small. In such a case, it's very unlikely. So suppose we are considering, let's say, Stockholm. Maybe 10 or 100 people have been infected, and we are assuming that we have a homogeneously mixing community. Homogeneous means that individuals are the same, but also that people mix the same. So if there are 100 people infected in Stockholm, which in the region of Stockholm, which has 2.4 million people, it's very unlikely that these two people will have an infectious contact with a third person, that both these two infectious people will have an infectious contact with the same other person. That's very unlikely in the beginning. So that is the important assumption why we're considering the beginning, because it's very unlikely then that two infectious people have an infectious contact with the same person. The consequence of this is that infectious individuals infect new people independently of each other. When this no longer happens, it is not independent, because if how many you infect then depends on how many have been infected by others. But now we assume that we're in the beginning, so infectious individuals infect new people independently. So that follows from this assumption. It can be done more rigorously, but anyway, then we have our epidemic behaves very much like a branching process. A branching process, that is a model where individuals give birth. So it is originally a model for giving birth, let's say for microorganisms giving birth, but in our case, giving birth corresponding to infect someone. And branching process theory says that individuals give birth or infect others independently from each other. So this means that in the beginning of an epidemic, assuming a large community that is homogeneous, new infections take place according close to a branching process. And then you can look in theory for branching process, which is a well-studied object since many years back. You can see what will happen with the corresponding branching process. And one of the important results from branching process theory, there are many results, but one of the important properties is that the number of infectious individuals, or in the branching process terminology, the number of individuals alive, but also the total number of infected, also those that have been recovered, or in branching process terminology, also the ones that have been born earlier but by now are dead. Both of these quantities grow exponentially at some rate r. So the number of infectives grow exponentially, and the total number infected also grows exponentially at the same rate. This can be proven. So here's a simple exercise. Suppose that we know that R equals 2.8 per week, and that we start with one index case, week 0. What is the expected number of cases after 1 week, 2 weeks, and 3 weeks? A very simple exercise. Here comes a slide. Here comes a histogram. On the y-axis, we have the number of cases. I think it is the cumulative number of cases, but it could also be the number of reported cases. The reason that I don't know that is that both will have a similar type of figure. No, it must be this is the number of the weekly number of reported cases or something like that, or bi-weekly or something. So it's not the cumulative, but the cumulative will also have an exponential growth rate. The important thing is that we see that here it looks like it is exponentially growing, which the theory also says. This was for Ebola. This is for the Ebola outbreak in 2014 and 15. These are the all three countries involved, whereas here we have the one for Guinea, here we have the one for Liberia, and here we have the one for Sierra Leone. So this is quite often the case that each sub-region does not, well, here it looks sort of exponential, but each sub-region typically does not look exponentially, but if you gather them together, they typically do look exponentially growing. This would also be the case if you took Sweden. So if this was all of Sweden, here you might have Stockholm, here Gothenburg, and here Skåne. So not all of them look exponentially, but if you gather them together, they look exponentially growing. So theory says that the number of infectives as well as the total number of infected should grow exponentially. And this quite often agrees with empirical evidence. So from this type of figure, how do we estimate the growth rate R? Well, as I said, both the number of infectives grow exponentially and the total number of infected, which is n minus the total number of susceptible, grows exponentially. The cumulative number of infected is, however, more robust, so I think it's better to use that one. And this S of t is declining, so n minus S of t is growing. So it's a growing quantity. So a simple estimate of R known is the following. If this holds, it follows that if we take two different time points, we call it T0 and Tk, then the ratio of the number of infected at time tk divided by the number of infected at time t0, and you take logarithm, that should equal to R times the time difference between these two measurements. So from this, we see that the natural estimator of R0 is equal to the logarithm of that ratio divided by the difference in time duration. You could do better if you do something called logistic regression, which I encourage people to do as well. So here's a simple exercise. Suppose all we have is 3 measurements. So from that, I want you to estimate what is the exponential growth rate, either using this simple estimator or using logistic regression. Okay, suppose now that we are in the situation that we have estimated the growth rate R. So we're in this situation. Here is the data, and we have estimated R. How about estimating the basic reproduction number? Can we do that? So is it possible by simply observing this growth rate, can we estimate the basic reproduction number? The answer is no. All we can say from this is that since it is growing, R0 must be larger than 1. So unfortunately, the connection between small r and R0 is weak. Should be not. It should be WEAK. This is the Malthusian parameter. Did I say this somewhere? I don't know if I mentioned that this. No, I forgot to mention that this parameter is called the Malthusian parameter. Okay, so anyway, this parameter R is called the Malthusian parameter. And the connection between small r and R0 is not that strong. Well, in some sense they're connected, but it's not that if you know one of them, you know the other one. Here's one explanation is that R is a rate, so it is measured in terms of something per week or something per day, whereas R0 is dimensionless. It's a number of people you infect during your infectious period. So it doesn't matter if you measure time in weeks or days, whereas here it does matter if you measure times in weeks or days. Here's another illustration that the two are not connected to each other that well. Consider the simplest deterministic epidemic model, which I said where the infection rate is beta and the recovery rate is gamma. And suppose that beta is 2 and that 1 over gamma, which is the mean duration of the infectious period, equals 1 week. Then R0 is beta divided by gamma, which is 2. We don't know what the growth rate is, but suppose it is R. And then consider another disease, which has beta equal to 1. So a lower transmission rate, but on the other hand, you're infectious for 2 weeks. So here, the second disease has a lower transmission rate, but a longer infectious period. So from this, we conclude that also here, R0 is equal to beta divided by gamma, which is 2. So these two diseases have the same R0. But clearly, the later one is slower since it happens, the infections happen after 2 weeks. So it's, well, you can just rescale time. From that, you will understand that the growth rate for the second disease is the growth rate of the first disease divided by 2. So here was a simple example having the same R0 but different Malthusian parameter R. So a question is, okay, can we say nothing? Can we say nothing from, can we say something about R0 from observing this? Well, yes, you can, but you need some additional information. So with some additional information and using branching process theory, we can connect the Malthusian parameter and the basic reproduction number. And we will do this by making use of the generation time distribution, which I talked about in my last lecture, lecture 3. Okay, here I call it R. So the growth rate is called the Malthusian parameter, and it depends both on the basic reproduction number and the generation time distribution. From branching process theory, it is possible to prove that Malthusian parameter is the solution to this equation. So if you know what R0 is, you know what the generation time distribution is, then the Malthusian parameter is the value R, which makes this equation equal to 1. in my last lecture, I talked about problems in estimating the generation time distribution. I will come back to that later, so we will see what consequences it has when we estimate R0. But as for now, I assume that it is known. For instance, an exercise is that suppose that the generation time follows a gamma distribution. I have not written down the gamma distribution here, and I'm not 100% sure that I can, so I will skip it. I encourage you to look it up in the Wikipedia, what the density for the gamma distribution looks like. Anyway, if you insert that, if you replace here by the gamma distribution with parameters alpha and beta, then this equation simplifies to this equation. So from here, it is clear that if we know what R0 is and we know what alpha and beta is, there's a unique R which solves this equation. So this idea has been or can be used to estimate R0, and let's do that for COVID-19. So in several papers, a common choice of generation time distribution is actually to assume that the generation time distribution follows a gamma distribution. So then it remains to determine which gamma distribution, and then this has been estimated using contact tracing and or other methods. And in one reference that I looked up, I actually I forgot which paper it was, so I don't have a reference for it, but you can look up in journals as well, and you will probably get slightly different estimates. Anyway, the one I looked at had assumed that the mean of the gamma distribution was 6.5, and the standard deviation of the gamma distribution was 4 days. Please note that here, alpha and beta are the original parameters of the gamma distribution, and this is not the mean and the standard deviation. Let me try to show this. If I remember correctly, I will show what the mean and the variance is. So I now share screen here. So if I remember correctly, so if X is gamma distributed with parameters alpha and beta, the expected value of X is alpha divided by beta, and the variance of X is alpha divided by beta squared. So the standard deviation, it does not have a standard notation, but let's write it like this. The standard deviation of X is always the square root of the variance of X. So it will be the square root of alpha divided by beta. So if this thing here, oops, let's see. Oops, I'm touching some wrong things here, sorry. So this thing was assumed to equal 6.5, and this thing here was estimated to equal 4.0. So these two together, then you have to solve this, that alpha equal da 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 and beta equal da da da. So that you have to solve. You have two equations. Here's one equation involving alpha and beta, and here's another one involving alpha beta. So this will give you a unique solution to what alpha and beta must equal. Okay. So let's see now. So assume that it's true that gamma has, the generation time is gamma distributed with mean 6.5, standard deviation 4 days. Then we would like to estimate the country-specific exponential growth rate using the cumulative number of case fatalities. So usually you don't know how many have been infected, but it's better, more informative data or more precise data on how many that died. And if the number of infected grows exponentially at rate R, the number of people that die also grow exponentially at rate R, because it's a certain fraction of them that die. So suppose we start the clock when 50 people have died, and we see how many have died 14 days later. Then our estimate of the exponential growth rate will look like this. So here is how many that have died after 14 days, and here is how many that have died the time we start our clock. It's typically not 50 exactly, maybe it's 52 or 56 or something like that. And then we divide by 14, since we're looking at a 14 day window. And I picked the data from Worldometer, which you can go. So what I've done here is hence used this estimator here. So here I had how many had died after 14 days, compared that to how many had died the day when I started the clock. 4 different countries. Why did I start when as many as 50 people had died? Well, the reason is that in the very early stage of an outbreak, things are very atypical. So usually strange things happen in the very beginning of an outbreak. But when 50 people have died, depending on what the true case fatality risk is, or the risk of dying, the number of infected people when this has happened is somewhere between 5,000 and 20,000. So it has sort of stabilized a little bit. So we're not in the very early part of the epidemic. I've done this for several countries. I will skip talking about Norway and Denmark because they had fewer case fatalities. So they are at the start of the clock when only 10 people had died. Otherwise, I would not get the reason why. And then why do I go only 14 days further on? Well, the reason is that after a while, preventive measures were put in place, and my estimate assumes no preventive measures. So the typical time frame is from the first half of March to sometime in the second half of March. By then, preventive measures had been put in place, but that would not have affected how many had died in the end of March, because typically the time of dying is 3 weeks after infection. So the people that died at the end of March, they were typically infected in the first part, maybe March 10 or something like that. So that was before preventive measures were put in place. So that's why I chose these time horizons. Then I've written down here the numbers that I found from Worldometer. Here is the estimate of the Malthusian parameter, and then the estimate of R0, which is obtained from here. So you solved alpha and beta using those equations, assuming that the mean was 6.5 days and the standard deviation was 4 days. And then we estimate the Malthusian parameters in the way I said, and then this gives you an estimate of R0. And here they are. So skip Norway and Denmark because that they were estimated at an earlier phase of the epidemic. And if I did the same thing for Sweden, actually the estimate of R0 would be 3.1. So they're not comparable. But these four are comparable. So we see that Sweden has the smallest basic reproduction number. Germany has larger, about the same size as Belgium. It's higher in UK and even higher in Spain. So an important message is that there is not one estimate of R0, but it depends on which country you consider. In fact, it not only depends on the country, it also depends on where in the country. So I write Sweden in quotation here because in the beginning, nearly all infected, or not nearly all, but the majority of infections took place in Stockholm and some in Gothenburg and Sörmland, south of Stockholm, whereas very few were infected up north of Sweden. So this estimate is not representative for all of Sweden, but mainly for Stockholm. So my guess is that if you go further up north in Sweden, the true R0 is smaller than 2.5. Similarly, these don't reflect all of the countries, but for instance, Spain, I know that most of the outbreak has taken place in Madrid, so this reflects more Madrid than all of Spain. Anyway, we see that it's a big difference. So the situation is worse in Spain because they have a higher reproduction number. This last column is how many you would have to vaccinate if you were to vaccinate before the outbreak comes, how many you would have to vaccinate in order to avoid an outbreak. So we see that we need to have vaccinated more in Spain than we would have needed in Sweden. But I will talk more about prevention later. Okay, so here is a description of the problem with estimating the generation time if you have biased in estimates of the generation time. And in my previous lecture, I explained that it is actually possible. There are several reasons why you actually do have biases in estimation of the generation time. All right, here it goes. So let I of t denote the incidence day t, so that is the number of people that get infected day t, which is more or less the same as the number of people infectious day t. If you're infectious for 5 days, then of course, yeah, it's not how many that are infectious, but it's the number of people that get infected this day. And so now we consider discrete time rather than continuous in my previous talk. But when you collect data, you typically only know the day. So then, how many will get infected on day t? Well, as I said, that depends on two things. It depends on R0 and on the generation time distribution. So if this is how many that get infected day t, then the number of people that get infected s days earlier is then I of t minus s. So here is a model, which in fact is very similar to the model I said earlier. But suppose we know the generation time and suppose we know the basic reproduction number, then the model says that on day t, how many will get infected? Well, that is a random quantity. It follows the Poisson distribution, and here is the mean of the Poisson distribution. So this model says that how many that get infected day t depends on how many were infected the earlier days, and then you have to must take the generation time distribution into consideration, and here is R0. So for instance, if R0 is 2, remember the example that I had earlier, suppose R0 is 2 and G of 1 is the same as G of 2. So the only possibility is that you infect someone after 1 week or after 2 weeks, and that happens with equal probability. Then how many that get infected today is 2 multiplied by 0.5 multiplied by how many were infected 1 week ago plus 0.5 times how many that were infected 2 weeks ago. So we see that if the generation time distribution has most of its mass, let's say, if we're talking days instead of weeks, if the typical generation time is 6 days, then the most influential number here is how many were infected 6 days earlier. But typically the generation time has probability mass over several days, so we have to take into account how many were infected not only 6 days earlier, but also 4, 5, 7, and 8 perhaps. And here is R0, the important parameter as well. So here is an exercise. Show that this equation here is more or less identical to the Euler-Lotke equation that I showed earlier. Anyway, this was the model. It can be used for two different purposes. Either we can estimate R0 if we observe the incidence up until some time, or else it can be used for predicting incidence if we know what R0 is. In both situations, we assume that we know what the generation time distribution is. So whether we do this, as is our case, or if you want to predict the outcome, in both situations, we need to know what the generation time distribution is in order to make progress with either one of these. How do we estimate the generation time distribution? Well, that I explained the last lecture, and I said it is done using contact tracing. So a question is then, okay, so if we insert an estimate of the generation time distribution, then the question is, what happens if our estimate is incorrect somehow? What happens to our estimate of R0 or of our predictions? Then I claim that it is easy to show that this mean quantity, the mean in the Poisson distribution, will increase if you replace the true generation time by an estimate which is smaller in mean. Similarly, this mean will also increase if you replace the generation time by an estimate which has the correct mean but has a larger variance. Larger variance is the same as the largest standard deviation. This is a good exercise to show this, either by means of simulations, numerically, or mathematically. It is shown in the paper by Scalia-Tomba and myself. Anyway, a consequence of these two results is that if we estimate the generation time in such a way that it is biased from below, we will underestimate R0. Similarly, if we estimate the generation time by something which has the correct mean but has a larger variance, then we will underestimate R0. The reason is that, why is that? Well, if we replace this by something which has smaller mean, then this thing increases. But on the other hand, we observe what we observe, so in order not to compensate for this increase, we have to replace the true value by something which has which is smaller than the true value. So that is why we underestimate R0. So we sort of, the effect of estimating this too small has the effect that this quantity in total becomes too big, but we observe the exponential growth rate. So then we have to compensate our overestimation of the whole quantity by replacing this by something which is too small. So that is why we underestimate R0. And the same applies if the generation time is replaced by an estimator which has correct mean but a larger variance, then we will also underestimate R0. And in the previous lecture, I told you about 3 problems with estimating the generation time from contact tracing. One was that when we look backwards in time, the effect was that we estimate the generation time from below. It was biased from below. I said that the mean of the generation time was underestimated. So then we are in this situation, so the effect is that R0 will be underestimated. Similarly, if we had multiple infector candidates and we just threw them away, the ones with multiple infector candidates, I said the effect was that the generation time was biased from below, or the mean generation time was underestimated. So it also has the effect that R0 will be underestimated. Finally, the effect of the serial intervals that we observed rather than the generation time. If you remember, serial intervals was the time interval between onset of symptoms rather than infections, because that we don't observe. The effect of that was that our generation time had too large standard deviation or too large variance. So the effect of that is that variance of G is overestimated. So then we're in this situation, it has the correct mean, but a larger variance. The effect will be that we also underestimate R0. So all 3 effects go in the same direction. All modeling makes some assumptions, but the hope is that the different errors go in different ways so that the overall effect is typically not so big. But here we have 3 effects going in the same direction. And if you remember, I told you in the previous lecture that it had fairly large consequences for estimation of R0 for the Ebola case. If I remember correctly, it was overestimated by about 25%. So you can see more about that in the paper that we had, that was cited in the previous lecture. Now, let me end by a few words about effective reproduction numbers, not how you estimate them. I think that is something that Mikael will talk about in the next lecture. So suppose that we have an epidemic model and we have an epidemic going, which is fairly well enough described by this epidemic model. And suppose that after some time, or perhaps right away, some preventive measures are put in place. For instance, that is the case with COVID-19. If you remember, the original model had transmission rate beta, but suppose now that the preventive measures, the total effect of them, it could be that we have a lot of different preventive measures, is that it reduces the contact rate by a factor C. So the remaining fraction of this contact rate is 1 minus C. So the new reproduction number is the old one multiplied by the remaining part of the contacts. So this is something which some people call the effective reproduction number. Other people use effective reproduction number for what comes on the next slide. So there is a bit of problems with the notation here. So I encourage you to be careful when you use the word effective reproduction number, because some people use this as the effective reproduction number, and some people also take into account immunity, which this one does not. Anyway, if we have this put in place very early or from the start, more or less, then it is not possible to have an outbreak if this new reproduction number is smaller than 1. And if you just look at this equation, when is this thing smaller than 1? That's the same thing as saying that C should be larger than 1 minus 1 upon R naught. Later on in the course, I and probably Michael will talk more about preventive measures, but today my focus is on the effective reproduction numbers, so I will not talk about consequences of this. Anyway, it could be that even if we have preventive measures, what I call the effective reproduction number in the start could still be above 1. Actually, I think it was above 1 in Sweden when we inserted the preventive measures because it continued to grow. But if this is the case, so the epidemic will continue to grow. However, it will grow slower than without preventive measures, but it will still grow since the reproduction number is still above 1. But then immunity builds up in the community, and it is only contacts with not yet infected people that result in infection. So after some time, the effective reproduction number is the original effective reproduction number multiplied by the fraction of susceptibles. So this, the first part here, is the number of infectious contacts you have with preventive measures. But after a while, when not everyone is susceptible, it is only the fraction S of T of those contacts that results in new infection. So the effective reproduction number sometime T later in the epidemic looks like this. It is the original one, basic reproduction number, multiplied by the effect of preventive measures, multiplied by the effect of the immunity in the community. So if the starting effective reproductive number is above 1, then the epidemic will grow. The effect will be that this thing starts decaying from 1, and eventually it decays such that this whole expression drops below 1. And when at this time point, when it is smaller than 1, or when it's equal to 1, let's say, then the epidemic will start declining. So I think in more or less all countries in Sweden, the current or the daily or the effective reproduction number now is smaller than 1. Definitely as in Sweden, because the number of cases is going down, perhaps not in every single region in Sweden, but on a national scale, it is definitely going down. So currently, our effective reproduction number is going 1, even if it was not in the beginning after preventive measures were put in place. So here is a comment on that. What is effective reproduction number? Some call this the effective reproduction number, whereas most people use this as the effective reproduction number. But perhaps a better word for this is called the instantaneous reproduction number, or the daily reproduction number, or the current reproduction number, just to indicate that we also take immunity into consideration. Okay, that was what I planned to say about effective reproduction numbers, and also how to estimate R naught, both from the final size and from the initial phase. So, thank you very much.